All right, howdy everybody. In this particular video, we're going to go over an electrophilic aromatic substitution reaction mechanism. And it's really kind of an advanced one. And the reason I say that is that the starting material in the product are reagents that are common to organic synthesis, but they're not commonly talked about in any of the standard organic chemistry textbooks. And so as the starting material here, we have what we call an I3 reagent. Sometimes these are referred to as hypervalent iodine reagents, and they're common oxidants that are used in a wide variety of modern organic reactions, but they don't typically appear in organic chemistry textbooks. The product of this is what we would call a diaryl iodonium salt, and it gets that name because this is basically an I+, and then there's a tosyl anion to balance it out. And it's drawn covalent, but we could easily imagine breaking that bond and giving the tosyl both of the electrons. And so neither hypervalent iodine reagents, whether it be the I3 oxidant or the diaryl iodonium salt, are common to organic chemistry textbooks. That being said, the fundamental steps of this reaction mechanism are going to almost explicitly follow the same mechanism for electrophilic aromatic substitution that you should be familiar with if you work through that chapter of your textbook. And because of that, we should be able to draw an analogy between this reaction and those reactions. So let me just remind you of what some of those reactions are. And perhaps we'll use the most classic example, which is bromination. So if we're going to take benzene, for instance, and FeBr3, and then treat it with Br2 to make bromobenzene, all of these mechanisms follow two steps. So the first step here is to make whatever our strong electrophile is, and then the second step is to do the EAS mechanism, the electrophilic aromatic substitution. And those, as long as you can follow that general recipe of some mixture of reagents are going to generate a very potent electrophile, and then that electrophile will do an electrophilic aromatic substitution, you should be okay. And so, of course, in this reaction, we take the Br2 molecule, and FeBr3 is a Lewis acid, and so we have some binding of the Br and now this is our activated electrophile. And so once we have the activated electrophile, then we can take our benzene starting material and it then can attack the electrophile. And so that generates FeBr4 minus. And here, remember, the minus is actually on the bromine atoms. We put it on iron as a way to keep track of the formal charge, but overall, the bromines are going to be more electronegative than the iron is. And so just be aware of that when we're putting formal charges in place, that it doesn't necessarily reflect the location of where that charge actually is. Okay, so then we end up with the de-aromatized intermediate. And so we have H and Br. And then now our H is going to fall off. Now we have bromobenzene. And of course, the H doesn't really fall off all on its own. It'll probably be pulled off by a bromine. And that'll then generate more FeBr3 plus HBr. Okay, and so this is really just kind of a review. And again, the important things here are to make our electrophile. And so this is E here. And so keep that in mind. And then our next step is to do the electrophilic aromatic substitution. And the EAS mechanism itself is always two parts. And so it's always attack of the benzene onto that electrophile. And then in the second step, we're going to re-aromatize by losing a proton falling off the benzene ring. Okay, so with that, we can return here to our desired reaction. And in this particular case, we have to use this TSOH to activate our starting material somehow to make a really good electrophile. All right, so we can start with that. Let me just redraw everything here. So I and then O. And I'm just going to draw out what AC is. And then we have CN. Now, one common thing that I've run into is when I put TSOH, a lot of students latch onto the OH and think it's an alcohol. But I'll remind you that TSOH stands for tossic acid, and it's actually a very, very strong acid. And I think about it as being the organic chemist version of sulfuric acid. And the reason I say that is because this part looks very sulfuric acid-like. This part here is really just to make it organic soluble. So sulfuric acid itself is very hard to get dry. And so often it comes as a solution in water at very high concentration. But here, this lipophilic benzene ring on the toxic acid part means that we can actually isolate it as a solid, and often it comes as the monohydrate. But monohydrate is, of course, better than having a lot of water around. And so as a strong acid, it's going to protonate things. And what I would encourage you to do is to think about these acetates as being basic on their oxygens. And so I'm going to have that get protonated. And if we have something that's positively charged, we of course have to make something that's negatively charged when we're starting with two neutral things. So toxic acid is neutral, and this iodonium salt, or sorry, this I3 reagent is neutral. And so overall, we need to make sure that we have a positive charge balanced by a negative charge, and that would be the tosylate anion. Now, this protonated carbonyl is a pretty good leaving group, so I'm just going to move those electrons up over like so. And that then will have acetic acid be the byproduct. And now we have what looks to me to be a much better leaving group, and especially if we balance out the tosylate here. So this I plus looks like a really great electrophile now. And so I'm just going to label this as E plus now for our EAS mechanism. Okay, so now if I take that, I can invoke the other starting material here. And now remember, the methoxy group is a really good ortho-para director. And so it shouldn't be surprising here that we're going to get the para-substituted product. So I'm going to start with this pair of electrons and work my way all the way over here to attack iodine. All right, and there we have our de-aromatized intermediate. What you'll notice, remember, is of course that there are a lot of resonance structures of this intermediate. I'm not going to draw all those out for this video because hopefully you're already familiar with them before you try to tackle one of these more advanced mechanisms. But I will remind you that this positive charge can get delocalized all the way into the oxygen lone pair up here. Okay, so then the second step of our EAS mechanism is to have that H plus fall off. Whoop. We still have our H plus here balanced with our OTS minus. And so technically that's still toxic acid. And now we're going to do a little bit of a ligand exchange on the iodine to really complete the product here. And I'm going to just take a minute to very quickly delete this and draw out that acetate more explicitly. Okay, so then this acetate is going to do exactly what we did before, where we protonate it. Like so. And then we're going to have it fall off the iodine and make some acetic acid. Now we have I plus, and we still have that OTS minus that I've tried to keep reminding you about floating around. And so that's just going to attack iodine to make the product. And there we go. So that is a electrophilic aromatic substitution mechanism that is pretty unusual for the standard organic 1, organic 2 curricula. But hopefully, if you we're paying attention to the key steps again and following this general outline that I have up here, where the goal is to make the electrophile and then to do the EAS, we can go through here and we can label this as being the electrophile that we made really only in 2 steps. So we protonated, which is very similar to binding the Lewis acid or protonating something else to make a very strong electrophile or a carbocation, let's say in a Friedel-Crafts reaction. And then it fell off. And so in many ways, this mimics the Friedel-Crafts alkylation reaction. We're just generating it on iodine. Okay, so then the next step here is to actually do the EAS mechanism. And again, once we have the strong electrophile, this is step 1 here where we have the attack of the aromatic ring onto that electrophile. And then step 2 here is just to re-aromatize. And then everything else after this is kind of special to this product where we end up swapping the acetate that's up here for the tosylate in the end product. But that's kind of really a subtle thing after the reaction. It's not really central to the EAS. Okay, so what I thought would be fun is now that we've talked about the electrophilic aromatic substitution, perhaps we can compare that to the nucleophilic aromatic substitution. And it turns out many times that these diaryl iodonium salts, again, so again, this is equivalent to I plus with OTS minus hanging off of it, and so that's where it gets the name diaryl iodonium salt. These end up being really great electrophiles for nucleophilic aromatic substitution instead of electrophilic aromatic substitution. And when I originally kind of thought about this problem, the reason I thought it was cool is because you put this ring on through EAS that we talked about before, but the other ring should be more electrophilic because we have a really good electron withdrawing group here. Electron withdrawing group. And so that means that this should be the ring that is more susceptible to a nucleophilic aromatic substitution. And so if we have nucleophile minus coming in, it can attack here. And we can swing these electrons over into the nitrile group. And then, of course, we can take those electrons and swing them back around. And when we do this, we can kick off iodine, but iodine doesn't want those electrons. Tosyl is the one that really wants the electrons. And so this overall fragmentation here, we would expect to generate then whatever our nucleophile is, has done the nucleophilic aromatic substitution on the nitrile containing ring. And since we started with nuke minus up top, we can end with something that's negatively charged below. So that might be something like tosyl. And then the final byproduct that you get out of it is iodoanisole, like this. And so what was fun to me about putting this one originally on an exam was the idea that students could engage both rings and take advantage both of a nucleophilic aromatic substitution and a electrophilic aromatic substitution in the same problem. So I thought that was pretty awesome. All right, if you're finding these videos helpful or at least moderately entertaining, please go ahead and subscribe to the YouTube channel. We really appreciate that. The number of subscribers helps us know that we're helping people and will give us encouragement to keep making these videos. Please like us, give us a positive comment in the feedback section. If you're really excited about these, feel free to find us on Patreon under Professor Carbon. Really appreciate any support. At the moment, this is pretty much just a hobby, but we'd like to make sure we can continue to make these videos for all of the chapters and content in the Organic 1, Organic 2 textbook. So please go ahead and subscribe, and hopefully you'll watch the next video. Thank you.